Hello, in this video I'm going to say a little bit about black holes, and I think this is going to be a tricky one because although we talk about black holes in pre-university physics, they come up on the curriculum. They're the end point of the life cycle of the supermassive stars, so they come up certainly in that point of view. We talk about them as being the center of a lot of galaxies. People are familiar with black holes as well, just generally in culture. They come up in films, they're in a lot of popular science books. They've got that exotic feel to them where people are quite intrigued by what actually happens in and around black holes. So there's something we talk about, but when it comes to actually describing them, the descriptions of black holes use mathematics that's way beyond what we can actually cope with in pre-university physics. So I'm going to have to try and walk a line here of describing black holes, hopefully in a little bit more detail and more usefully than comes up in some of the textbooks for your A-level physics or something like that. But I'm going to have to do it without using any mathematics because we're just not ready for that yet. And it really isn't simple mathematics, even from an undergraduate or graduate physics point of view. It's not something that you're going to be doing first term or first year in your undergrad if you go off to do a physics or an astrophysics degree or something like that. I don't think I did my detailed mathematical treatments of black holes until actually I think it was in my master's year, I think, really, in an astrophysics degree. So it came quite late on when really looking at them in detail. Okay, you're building up the maths over the preceding years, but it's not something that you'll be doing early days, I wouldn't have thought, in a physics or an astrophysics degree. So it's quite complicated mathematics, relatively speaking, at least for graduate level science. So let's see how I get on anyway. It might be a bit hand wavy, but I'm going to try and bring in a few of the terms that get used for describing black holes and look at some of the history. So starting off with the basics then, I mean, as I'm sure you're aware, I mean, black holes, these are massive, compact objects. So they're very, very dense. They've got mass in very small volume of space. Some might say in no volume of space. This is where we get onto the idea of a singularity, where you've got a point in space, no volume, but all of the mass. So we're saying that we've got some kind of singularity. This is a term that comes up a lot when describing black holes. This is our infinite density. So density, our mass over volume. And we're saying, right, this is infinite. We've got zero volume. Now, this is already raising something that you'll want to think about if you start doing undergraduate work or postgraduate work in astrophysics and you're looking at black holes. What exactly is the descriptive power we've got over a singularity? Is this something that we're happy with, talking about this infinite density, or do we need some other way of describing this? So I'll leave that hanging already. But this is what we're talking about with singularities, this point of infinite density. And yeah, so we've got this object, this black hole, where we've got this singularity, and it's so dense that if you get close enough to this singularity, nothing can escape it. The effect due to gravity of this singularity means that even light, the fastest moving thing in the universe, even light can't get away. And this is feeding into at least something conceptually familiar to us, even if we can't do the maths. We've spoken about escape velocities in previous videos. We looked at escape velocities of the Earth. Okay, we did all of that within the realms of classical mechanics. So not the maths that we can use and apply to black holes. But conceptually, we were saying, yeah, okay, if we want to, we've got a certain amount of mass here. We've got the Earth, we've got a certain amount of mass, and we want to escape from that mass, and we're at a certain distance from the center of that mass. What is our escape velocity? That was what we were working out with escape velocity. So it's not a big jump to say, well, if the fastest we can move is the speed of light, how do we get to the situation where we have an escape velocity which is equal to the speed of light? Clearly, we've got some kind of threshold here. If we reach a point where escape velocity equals speed of light, then we have a threshold condition. On one side of it, things can escape, and on the other side of it, things can't escape. So conceptually, at least we can deal with that in our world of classical physics. Now, historically speaking, this is how people really started thinking about black holes. Yeah, we're going back to the 18th century here. You can go a long way back. So 50 to 100 years after Newton, and we can say they knew more about how gravity was working. You know, we had Newton's theory of gravitation and what was going on there. Light was being thought of as a particle at that time. So this is very much classical mechanics. We got some particle that can move up to a certain speed. We have a description of gravity. When do we hit this limiting case in escape velocity? So that was when the idea of a black hole came into existence. Black because that's when we get to the point where light can't get out, so it appears black. Now the talk died down a bit in the 19th century because then light was being described as a wave. We've got the wave nature of light. We've got electromagnetic waves. No one really knew what to do with this in terms of the effect of gravity on waves. So there was, okay, we need something new here. We need a new way of describing what's going on now that we've got wave nature of light. Roll on 20th century. So early 20th century, we've then got Einstein putting together his theories of relativity, special relativity, or probably more relevant to this one, we've got general relativity. And this is where he's pulling together space and time into space-time and showing the limitations of classical mechanics, Newtonian gravity. We can't then describe these extreme cases where we've got very high speeds and very high masses and these high densities. It all starts breaking down. All of our classical physics, our Newtonian mechanics and all of that, Newtonian gravity, is just not good enough anymore. It's not describing what's actually happening. And general relativity is what Einstein was pulling together in order to describe gravity around these very high density objects. And special relativity is then, looking at things like, things that are moving at the speed of light. So we've got all of this new description going on, which means we can then start answering these questions that were unanswered in the 18th and 19th century. And part of all of this is Einstein set up a whole load of field equations. So equations describing fields, whether they're gravitational fields, electromagnetic fields, or whatever. He set up all these field equations. Loads of people were then solving these. So in the 1920s, you've got people like Carl Schwarzschild. In the 30s, you've got Chandrasekhar. These are people that we're familiar with in our pre-university physics. They get mentioned. And they were solving these equations to look for these threshold conditions. So much like we had a threshold condition here, looking at escape velocity being equal to the speed of light using classical physics, here we get a whole new load of threshold conditions in modern physics. So these are threshold conditions that are actually going to reflect things that are happening in the real world around these black holes. So new load of threshold conditions. And this is then revealing different domains of description. So when we're talking about black holes, we're getting this new dividing point between, can we escape the black hole or are we inside the black hole? Are we in it never to get out, or are we outside it with a possibility, particularly if we're moving at the speed of light, of escape? So these are the threshold conditions, these sort of things that are then being found in these field equations. So this is given another one of these descriptive terms that comes up a lot. So event horizon. This is one of these threshold conditions that's used in the description of black holes. As in, if you are, depending on which side of the event horizon you're on, do you have the possibility of escaping the black hole or not? So if you are inside the event horizon, Well, there's only one way you're going, and that is into the black hole, and you're going further into the black hole. As this is all described in relativity and space-time, all these descriptions brought together. And things change when you cross the event horizon. When you're inside the black hole, the singularity, that is now your future. That is where you're going to. There's nothing you can do about it. You think about our everyday life outside of black holes, we know that we can't change that we're moving forwards in time. So tomorrow is our future. There's nothing we can do about that, but we can move around in space. When you're inside the black hole, it's like these things have switched. So the position of the singularity at the center of the black hole, center has got a sort of different meaning to it now, because when you're inside the black hole, that center is your future. So just as tomorrow is our future in terms of time outside the black hole, when you're inside the black hole, the singularity, which we think of as being a point in space, is then your future. So it's like we flip those things over, that now a point in space is something that we can't avoid in the future rather than a particular time. So we're getting this change in mathematical description. And this is reflected in these field equations. You can see this sort of like flipping of the space and time descriptions. It's like they've swapped over in some way. Okay, it's a simplified way of putting it. But these are the sort of threshold conditions that people are spotting. But still, long and the short of it with event horizon is it's giving that dividing line really between inside a black hole and outside a black hole. And you get all manner of weird effects that are happening when you're getting closer and closer to the event horizon, because you're getting all of these relativity effects, things to do with time dilation and length contraction and things like that, which are happening around this point, this surface in space, the event horizon. So that's another one of these things, along with singularity, that you'll hear one of these terms that gets used when describing black holes. The another one, I suppose it fits in with event horizon. I might as well mention now Schwarzschild radius, which comes up, fits in with event horizon. So if you've got a non-rotating black hole, then we've got our singularity, which I'll represent with this dot, but of course it'll be a dot that's got no volume to it. And you've got an event horizon, which is a sphere around this singularity. And then the radius of this sphere for a non-rotating black hole is the Schwarzschild radius. So the sphere is the event horizon, the dot in the middle is the singularity, the radius of the sphere is the Schwarzschild radius. And that's for just a simple non-rotating black hole. That's our basic terminology for describing these things. And this Schwarzschild radius, we can work this out. If you conceptually, as we did here, talk about the escape velocity being equal to the speed of light, then remember when we were talking about the escape velocity from the Earth, well, it depends how far away you are from the center of mass. So we considered in our classical physics the Earth to be just a point. It's a particle with at the center of mass with a particular mass, and depending on how far away we were from that center of mass, we had a different escape velocity. Because the escape velocity, remember, we're trying to overcome that or replace the negative gravitational potential energy. That was how we were thinking of it in terms of classical physics. We want to get back to infinity, back to that infinite distance from the mass where our gravitational potential energy was equal to zero. So the further away we start from the Earth, the lower the escape velocity we need. So escape velocity is a function of the radius. It's a function of the distance away from Earth imagined as point mass. So if our escape velocity varies with distance from the center of mass, there's going to be some distance from that center of mass where the escape velocity is equal to c, the speed of light. So if we can get all of the mass of the Earth inside that radius, then we've got ourselves a black hole. Now, for the Earth, that means compacting it down to, well, it's millimeters. I don't know the exact number, but you're getting all of the mass of the Earth and squeezing it into something smaller than a thimble, essentially. And then you can say, okay, if we're sitting on that thimble, which has got the Earth squeezed into it, then we're not getting away, even if we're moving at the speed of light. So that's what we're getting at here for the Schwarzschild radius. That's where we're creating, for a particular mass, that's where we're getting the escape velocity being equal to the speed of light, as calculated using relativity, not using classical mechanics and Newtonian gravity. Right, so that's all of those key terms. I mean, what other properties do black holes have? They've got angular momentum. I mean, I mentioned that black holes, they often rotate. These basic descriptions, the coinciding of the event horizon with the Schwarzschild radius, that's for a non-rotating black hole. Angular momentum is conserved in these black holes, so they will often be rotating. Obviously, they have a mass, which we need. They also have electric charge, that's conserved as well. So you can have we can have charged black holes. So we've certainly got that. In terms of detecting them, because the other information is widely believed to be lost when it goes inside black holes, but it's an area of active research. What information is maintained, does actually continue. If something crosses the event horizon, how much of the information about that object is actually lost? This is getting into the depths of some pretty meaty theoretical physics, and it's still active research. In terms of detecting these things, well, we have a problem of detecting a black hole directly because it's black. So it's really detecting them indirectly through objects and matter that are going to be around the black hole. So if you've got matter nearby, it will accrete around the black hole. And some of it might be falling in. You'll have a lot of it just orbiting around. You get these disks or spheres, but often disks, rotating around these black holes. There's a lot of energy there because you can have a lot of matter. Some of it's going to be falling inwards. So you can get a lot of release of electromagnetic radiation. And then we can actually observe these accretion disks. You'll often get jets of matter as well. So you might have a disk, and then you'll have the black hole, and then you'll have these jets coming out perpendicular to the disk. And you can often observe these as well. So there's a lot of energy around. You just need to have some matter outside the black hole in order to be able to observe this energy in effect. And you get things, there's the Event Horizon Telescope. This is a radio telescope specifically set up for this task. And there's other observational equipment as well, which observe these sort of things. So, yeah, there's still a lot that's unknown about black holes. Same in terms of their formation. We've been talking about black holes being formed from the gravitational collapse of these supermassive supermassive stars. So they've gone through the white dwarf stage, where you've got this white dwarf which is being held up by the electron degeneracy pressure that's adding the outward push to resist that inward pull of gravity and holding these less massive stars at white dwarf stage. Some of them, again, they collapse beyond white dwarf, and they get down to neutron degeneracy pressure, and you get a neutron star. But then if there is enough matter there, it just continues to collapse. The force due to gravity just can't be stopped, and it collapses down to this singularity, and then we've got ourselves a black hole. So that's the main way that we're describing black holes in our pre-university physics. People speculate other mechanisms for the formation of black holes, particularly when we start looking back into the early universe and some of these cosmological models that are built for how things formed and evolved in the early universe. These are somewhat speculative. I'm not going to get into all of that here, but there's again, it's another area of active research. So there's a lot of work being done here. You'd have heard stuff about possibly black holes evaporating and things like that, whether Hawking radiation, named after Stephen Hawking, of having black holes not being entirely black. Actually, they are very, very slowly emitting radiation in some form. So that's another active area of research. And then you get all these wild and wacky things, things like wormholes and white holes and things like that. There's all manner of stuff that people can push the maths towards. Is it real? Is it not? This is something that people still deal with in theoretical physics nowadays. But I'm going to leave it there, of having done a historical sweep of black holes and then at least spoken a little bit about singularities, event horizons, Schwarzschild radiuses. So hopefully that's at least whetted your appetite for the sort of thing you might be looking at if you study black holes in more detail in the future.